Welcome to BKW Physics. I'm Mr. McConnelly, and today we're going to talk about fusion. Now we've already talked about fission, and fission is when you take a big element, you break it into pieces. But this time we're going to combine two small elements into one larger element. And my example for today is deuterium and tritium being combined. Deuterium, the 2, tritium, the 3, they're both hydrogens. What that yields is helium and a nitrogen. Now let's do some really quick math here. Really quick math says if you add up the tops on the left-hand side, you got 5. If you add up the bottoms, you got 2. Right-hand side, 5, 2. Balanced? Question mark? Answer?
Yes.
No. The reason is, remember, these are 2.001, I'm making up the numbers, 3.002. They're not exactly whole numbers. And because they're not exactly whole numbers, when you actually if you were to add this in detail, take it out, 5 places to the right of the decimal point, these would no longer equal each other. And it'd be considerably far off, actually. So, the heavier side the heavier side is the left-hand side over here. And so in nature, in physics, they have to be balanced. This has to balance somehow. And since they're different, there is a difference. This is called a mass defect. Mass defect means the two sides are different, right? What does mass defect end up resulting in? Binding energy. That's the words I was looking for. So mass defects ends up being binding energy. In other words, since the masses aren't quite equal, the way nature makes this equal is by putting energy on one side to balance out the equation. Now, how much energy are you talking about? Well, in this case, to make this balance, you need 17.6 mega electron volts tacked onto this side. That particular number will make it work out. Now, what does all the math go back to? What equation governs this mass-energy relationship here? Right. Equals mc squared. So, if you were to do the math exactly, and you were to take it out 5 places past the decimal, you would find that there is a difference in mass. That number could be plugged in here, and you would get energy. What units would the energy be in? They would be in joules. Thank you. So it's going to be a number of joules. This number is in electron volts. How do you get from joules to electron volts? I'm just taking you through the process. This is not going to be like a Regents question or anything. I'm just trying to take you through the thought process of how I got from this idea to that number. So I did E equals mc squared. I got a certain number of joules. That certain number of joules then can be converted, and there's a conversion factor between joules and electron volts. Front page of your reference table says
1 electron volt is equal to 1.6 e negative 19 joules.
Right. So you basically divide by 1.6 e negative 19. Woof, that takes you to there. The m means what? Mega, which is how many?
10 to the 6th.
Yeah, 10 to the 6. So you got 17.6 times 10 to the 6 electron volts. You can see it's a pretty big number. All right? You're in the million billion category. Now, just as a comparison here, because comparisons always help. As a comparison, a stick of dynamite, no, back up. A molecule in a stick of dynamite gives you 20 electron volts. This is a molecule in dynamite. A molecule in this reaction, we'll call it helium molecule. How much does it give you in comparison? This is one molecule in dynamite. This is one molecule in our fusion reaction. You see the difference? Most people can think of dynamite as, well, it's pretty explosive. You can blow stuff up. It's really impressive. Well, this makes it look like a joke. Okay? Pound for pound, this is one of the most nasty, volatile things you can do. Okay? It's a fusion reaction. It creates a huge amount of energy. Our examples of where you might see this: a star or our sun, any star. There's also this thing called a tokamak. It's a reactor. And an H-bomb. Those are three clear examples of where you might see this sort of fusion reaction happening. So for fusion, for physics, that's it for today.